Oh my gosh, where's Tamara? I need to find her. We really need to get this project done. Tamara, where are you? Maybe she's in here. Ah, there you are.
Oh, hi. So today we're just going to touch base on different topics. The first one is going to be wavelengths of light. So when an atom or an ion absorbs energy, its electrons make transitions from lower or the lowest energy level, known as its ground state, to higher energy levels or excited states. This is known as a quantum transition. The larger the transition, the higher amount of energy released, and the shorter the wavelength. In this case, the energy absorbed is in the form of heat or electromagnetic radiation. All electromagnetic rays travel at the speed of light, c, which is 3 times 10 to the 8 meters per second. Therefore, visible light is an example of electromagnetic radiation. Different wavelengths indicate different color spectrums. E equals H times C divided by lambda. E is the energy of a system in joules. H is Planck's constant. His constant is 6.626 times 10 to the negative 34 joules second. C is also known as the speed of light. The speed of light is 3.0 times 10 to the 8th meters per second. And lambda is just wavelength. And wavelength can either be in meters or nanometers.
Given the wavelength ranges based on the color spectrum, we can approximate the energy of each colored flame. So for the violet calculations, we don't have a purple marker, so we're going to go ahead and use black. But E equals H times C over lambda. And for the violet color, the wavelength range is 390 nanometers to 455 nanometers, but we're going to use the select value of 450 nanometers. And we have to convert that to meters, which is shown by 4.5 times 10 to the negative 7. And once we make those calculations, it is 4.417 times 10 to the negative 19 joules, which is the energy of our system.
Okay, so now we will be calculating the energy for the blue color wavelength. So the blue ranges from 455 nanometers to 492 nanometers. We'll be using the select value of 470 nanometers. 1 nanometer is a billionth of a meter, so we will convert that to meters by multiplying by 10 to the negative 7th. And the answer we will receive is 4.230 times 10 to the negative 19th joule.
Green light ranges from 492 to 577 nanometers, and we are using the select value of 500 nanometers, which converts to 5 times 10 to the negative 7 meters. When we make our calculations, we get that our final answer is 3.976 times 10 to the negative 19 joules.
For yellow, the range of wavelength is from 577 nanometers to 610. Our select value is 600 nanometers. Convert that to meters, and we will receive 3.313 times 10 to the negative 19th joule.
For orange light, we have 610 to 650 nanometers as the range, and we selected 650, converted that to meters, and got 3.058 times 10 to the negative 19 joules.
For red, the range is 650 through 780. We chose 700 nanometers to conduct our calculations with. We converted that to meters, and we got 2.840 times 10 to the negative 19th joule. In our experiment, we used alcohol, lithium chloride, copper sulfate, strontium chloride, magnesium nitrate, potassium nitrate, and calcium chloride. Alrighty, so we put approximately the same amount of each salt into each watch glass. We have 7 watch glasses total, the 6 chemicals, and 1 watch glass just being pure alcohol. We're going to add a few drops of alcohol to each watch glass except for the one already containing the alcohol. The watch glass containing the alcohol will be used as our control variable just to see what color alcohol burns already. Now we're going to mix all the salts with the alcohol using a stirring rod just to make sure everything is evenly distributed.
So next, we light the alcohol and salt mixture.
So if we're looking at our second watch glass, which is our first salt or lithium chloride, we see that it's burning a violet purplish color, indicating that it is approximately 400 nanometers, and it approximately released 4.417 times 10 to the negative 19th joule.
And our last watch glass, which contains calcium chloride, is burning a red flame, which indicates that the wavelength is about 700 nanometers. From our calculations, we have found that it releases 2.840 times 10 to the negative 19 joules.
Combustion is a chemical reaction between substances. It usually involves oxygen and is accompanied by the generation of heat and light, or flames. At higher temperatures, chemicals react and generate more heat than can escape into the air, which is why they burn with a flame. When equilibrium between the total heat energies of the reactants and the total heat energies of the products are reached, combustion stops, and a flame goes out. As previously stated, the emission of light and flames result from excited particles or electrons jumping from their ground states to states with higher energy levels. And fire is the combination of heat and light from the combination of oxygen and other materials. The flame or light is composed of glowing particles of burning material and numerous gases.
Combustion is a type of oxidation reaction, and oxidation means reacted chemically with oxygen. Oxidation is an exothermic reaction, which means that it releases heat. Common three oxidation reactions that release energy known as heat and light is C plus O2, which yields CO2, carbon dioxide, 2C plus O2, which yields 2CO, which is carbon monoxide, and 2H2 plus O2, which yields 2H2O, or water. Yo, what's good, Tamara?
Hey, Summer. I have a joke for you, a few chemistry puns.
Let's go.
Why does hamburger yield lower energy than steak?
I don't know why.
Because it's in its ground state.
Oh, you slapper. Okay, I got one. What did they do with the dead chemist?
What?
They buried him.
Barium. Wait,
barium.
B-A-R-I-U-M.
B-A-R-I-U-M. That's how you spell barium, right?
Valid.
Okay.
I have one. This is for you, Miss Lula. My teacher threw sodium chloride at me. That's a salt. Okay. Wait.
Yeah.
Class of
2017.
My hair.
Bye, Miss Lula.
Bye, guys. My hair got